Okay, Matt Roscoe here again at the University of Montana, and a continuation of our lecture on Chapter 10 on the revival of number theory. So let's talk a little bit about Leonhard Euler. He was the son of a Lutheran pastor. He was influenced by Nicholas and Daniel Bernoulli to pursue mathematics, and he spent time at the Academy of St. Petersburg and the Berlin Academy. He is, without a doubt, the most prolific and versatile writer in all of mathematics history. Mathematical contributions were wide and encompassing. Euler established the notation for pi, e, and I. He developed calculus and differential equations. He had the first series expansions of e, cosine x, and sine x. He's known for the Euler identity, and he also contributed to graph theory. But one of the things Euler also worked on was perfect numbers. And he proved the converse of Euclid's theorem on perfect numbers. He said if n is an even perfect number, then n is of the form 2 raised to the k minus 1 times the quantity 2 to the k minus 1, where 2 to the k minus 1 is a Mersenne prime. Perhaps it would be worth thinking a bit about, how this compares to what Euler's original statement, Euclid's original statement was, just to remind us. Let's see here. Let's see. Here it is. So on slide 8, we see that if we have 2 raised to the k minus 1 as a prime, then we have this as a perfect number. And I guess what we can think of is what Euler did is said, if we have a perfect number, and he added the stipulation that it must be even, then the perfect number will be of this form. And I hope that you can see that, Euclid's theorem only provides even perfect numbers, right? So it sort of leaves out to anyone's guess whether there are some odd perfect numbers, and it turns out nobody actually has a proof for that yet. That's an open question in mathematics. It's assumed to be no. The answer is assumed to be no, that all perfect numbers are assumed to be even, but no proof of that assertion exists. So let's talk a little bit about how this looks as a proof. It's quite a tour de force. So I will turn on my Elmo cam and we'll talk a little bit about this. Let me make this larger. Let's see if I can get it a little bit bigger. So I'll make a copy of this and make sure you have it. But the proof we're trying to prove is that if n is an even perfect number, then n is of this form, where 2 to the k minus 1 is a Mersenne prime. So this guy right here, 2 to the k minus 1, is a Mersenne prime. So here's the proof. Examine numbers in the form 2 raised to the k minus 1 times n. This is some arbitrary even number. So let m be odd and let k be greater than or equal to 2. So the question is how many factors does it have? So we suppose that 1, d, d2, all the way up to m are the divisors of m. So m has some divisors. We don't know really how many there are. So then we can think of the numbers of divisors of n being equal to sort of this 1 plus 2 squared all the way up to the k minus 1, right? Times 1 plus d1 plus d2 plus all the way up to m. So we can kind of see that that this number right here is just, of course, the number of factors of m associated with m. And this is a geometric progression, right? So the geometric progression sums to the number. We did this in class. Geometric progression can be simplified to 2 raised to the k minus 1 times sigma of m, which is the sum of m's factors, right? So now think about this. If n is a perfect, then what we know is that sigma of n is going to be equal to 2n, right? And sigma of n is going to be equal to 2n, and it's also equal to 2 times the k minus 2 raised to the k minus 1 times m. Okay. Setting these results equal, right? So we know that sigma of n is equal to this guy and sigma n is equal to this guy, right? We have 2 raised to the k times m, this result, equal to the first result, which is 2 raised to the k minus 1 times sigma m. So by the fundamental theorem of arithmetic, we know that if there's a factor of 2 raised to the k minus 1 on the right-hand side, there must be one on the left-hand side. And this guy, of course, is prime. So this prime must divide that number. But since 2 raised to the k and 2 raised to the k minus 1 are relatively prime, right? Anytime we have consecutive integers, they are relatively prime. That's Euclid's lemma. We have, so since these guys, 2 raised to the k and 2 raised to the k minus 1, they're consecutive integers, and this guy divides this side, but these guys are relatively prime. Well, what we can say then is that this must divide m, right? All right. So let's say that m is equal to, this little m is equal to this factor times some other number m, where m is an element of the positive integers. If we substitute that into 1, if I go back to 1, here's 1. We're going to substitute m is this thing, right? So I'm going to substitute in for this m. We get this. 2 raised to the k times 2 raised to the k minus 1 times m must be equal to 2 raised to the k minus 1 times sigma m. Which, when we divide the common factor out left and right, what do we get? We get 2 raised to the k times m is equal to sigma m. And because both m and m, large M and little m, are divisors of m, with, let's say, m has to be smaller than m, we can say what? We can say that 2 raised to the k times big M must be equal to sigma m, and that has to be bigger than m plus m, so small m plus big N, equal to 2 raised to the k minus 1 times m plus m, which is, of course, right, this guy, 2 raised to the km. So what have we shown? We've shown that this guy must be equal to m plus m. So why is that? Well, the reason is because we get to the same spot on both sides here, right? And these are equals, right? So the only way it could be true here in the middle, right, is if this was an equality. So this sigma m must be equal to m plus m. Okay, so sigma m must have only 2 positive divisors, m and m. So therefore m must be prime. And m, big M, must be 1. So from 2, if we go back to 2 up here, we know m has this form. Here's 2, right? 2 raised to the k minus 1 times 1, right? And m must be equal to 2 raised to the k minus 1, some prime Mersenne. So it's a Mersenne prime. And if it's a Mersenne prime, then n equal to 2 raised to the k minus 1 times m, which is 2 raised to the k minus 1 times k, 2 raised to the k minus 1. This guy has to be a perfect number. And thus, with 2 raised to the k prime, completes the proof. So certainly a strong showing by Euler that the converse of Euclid's theorem for perfect numbers, offered some nearly 2,000 years later, is indeed true, that if you have an even perfect number, then the even perfect number has to be of this form, and all even perfect numbers employ some Mersenne prime in their construction. All right, let's move on and talk about Gauss. So Gauss was a remarkable childhood prodigy. His abilities attracted the attention of aristocratic sponsors, and he secured a position at the University of Göttingen in 1806. He made contributions in virtually every branch of mathematics. Um, for example, he looked at constructible polygons. He has a method of least squares. He's the one who gave us the fundamental theorem of algebra. He made contributions to theoretical astronomy. He discovered Neptune as a planet, but he's also known for his contributions for number theory. Among those, probably he's most known for introducing the theory of congruences, greatly expanding the mathematical tool set for number theory investigations. So the way that I think I can best explain this to you is to have you read your book and also to take a look at the handout I prepared. In 1801, Gauss proposes this theory of congruence, and he defines some things and then puts forward some theorems about congruences. So let's look first at what it means to be congruent. It says, let n be a fixed positive integer. Two integers a and b are said to be congruent modulo n, symbolized by a triple equal sign b, or what we call congruent b, mod n. If n divides the difference, a minus b, that is, if a minus b can be written as kn for some integer k. Okay? And he goes on to say, well, if a and b are congruent mod n, then they're congruent mod n if and only if a and b leave the same non-negative remainder when divided by n. So let's take some time and think about congruence here and prove this theorem. So he says that a is congruent to b mod n if and only if a and b leave same non-negative remainder when divided by n. So we have to prove this two ways, right? If this is an if and only if, so let's go forward first. We can say that a is congruent to b mod n. What we want to prove is that it leaves the same remainder, non-negative remainder, when divided by n. So if a is congruent, then n divides the difference. And if n divides the difference, then there is some k in the integers that we can multiply n by to equal a minus b. So if we solve for a, what that says is that a is equal to b plus kn. And by the division algorithm, we can say that b is some, when divided by n, is some qn plus r, where r is between 0 and n. So this b can be written as some quotient of n plus remainder. And if we combine those results, we get that a is equal to b plus kn. Substituting in our expression for b, we get a qn plus r plus kn, which is a q plus k times n plus r. So what does that mean? That means a leaves remainder r as well, because we have it written as when divided by n, because we have a written as some quotient of n plus r. So a leaves the same remainder as b, and we've proven it forward that a and b leave the same non-negative remainder. So now let's prove it backwards. I guess sufficiency, this is necessity, sufficiency. So if we suppose a and b leave the same remainder, then they must be congruent, is the idea. So here we have a and b both written as some quotient and remainder, but the remainder, of course, is the same. The quotient could be potentially different. So maybe I should say for some q1, q2 in the positive integers, I'm just thinking to myself, I don't think that necessarily has to be positive, so in the integers. So then a minus b, if I construct the difference here, then what do we get? We get the q1n plus r minus the q2n minus r, which we would call q1 minus q2n. And what we can see is then n divides the difference here, because n times some integer, this is certainly an element in the integers, n times some integer is equal to a minus b. So n divides the difference. If n divides the difference, then they're congruent. So indeed, two integers are are congruent mod n if and only if they leave the same non-negative remainder. After producing that theorem, he produces all kinds of other nice theorems to go along with that can be used as tools. You know, A is congruent to itself if A is congruent to B and B is congruent to A. If A is congruent to B and B is congruent to C, then A is congruent to C. So this is transitivity. And then 4, if we have A congruent to B and C congruent to D, then what? Then A plus C and B plus D are congruent, and A times C and B times D are congruent. Finally, 5, if A is congruent to B mod n and A plus C, then A plus C and B plus C are congruent, as well as A times C and B times C. So we can add or multiply by constants and maintain congruence. And then lastly, if A is congruent to B, then A to the k is congruent to B to the k for any positive integer k. So he's developing here an algebra for congruency. Let's go ahead and prove property 4a. So I'm going to think of 4a as this part. So if A is congruent to B and C is congruent to D, then A plus C is congruent to B plus D. Let's take a look at that one. See how a proof might look. So let me make it a little bit bigger. So if A is congruent to B mod n and C is congruent to D mod n, then what we want to show is that A plus C is congruent to B plus D mod n. So let's let A be congruent to B. Well, that means then that n divides the difference, and that also means that there is some k1 times n that must be equal to the difference for that k1 in the integers. And if, let's see, C is congruent, this is supposed to be a C, is congruent to D, then n must divide the difference, so n must divide C minus D. So then there's some k2 times n that is equal to the difference, so k2 element of Z. So now if we take these two guys and we add them together, we get k1 plus k2, we get A minus B plus C minus D here. Factoring out the n, we get k1 plus k2 times n. I guess adding the two positives and associating the two subtractions together, here we get A plus C minus B plus D. So what does this show? This shows that n times some constant equals the difference here. So thus n divides A plus C minus B plus D. So if n divides this, then these two guys must be congruent mod n. And that's the proof for property 4a. So this sheet is available to you as sort of a cheat sheet for some of the problems in the chapter. But let's talk about where this gets Gauss. It gets him able to show all kinds of crazy things, such as this problem. So show that 5 divides this sum 7 times 16 raised to the n plus 3 for all n. Let's take a quick look at how that would work. Large. So if we recast this incongruence, what we want to show is that this number is congruent to 0 mod 5, right? If that would mean that 5 would divide this difference, right? Which would mean 5 would divide that number, because the difference between this number and 0 is just that number. So what we really want to show is that 7 times 16 raised to the n plus 3 is congruent to 0 mod 5. So let's just note that 7 is congruent to 2 mod 5, right? And 16 is congruent to 1 mod 5, right? So that would mean that 16 raised to the n, this number in the problem, is congruent to 1 raised to the n if n is greater than 0, right? We have a theorem for that. That's, I guess, this theorem right here. And so that's just a 1 mod 5. So therefore, what can we say? We can say 7 times 16 raised to the n Well, 7 is congruent to 2. We can replace it with 2. 16 raised to the n is congruent to 1. We can replace it with a 1. So it's congruent to 2, right? Mod 5. So I'm going to call that result 1. Since 3 is congruent to 3 mod 5, we have by adding, so we need to know 3 here, right? By adding 1 and 2, we'd add this to this, and we get this. We'd add 2 to 3, and we'd get 5. And 5, of course, mod 5 is congruent to 0, because 5 leaves remainder 0 when divided by 5. So what we've shown is that this number, 7 times 16 raised to the n plus 3, is congruent to 0 mod 5. So 5 must divide the difference, and 5 must divide 7 times 16 raised to the n plus 3 for all n greater than or equal to 0. So you can see that even sort of strangely complicated problems here, we're talking all n will fall quite easily using congruence theory. And it turns out that this allows Gauss to prove that every even perfect number will end in either a 6 or 8, which was something we had noticed before in class when we looked at perfect numbers generated by Mersenne primes. So let's take a quick look at that and end. So let's see, all even perfect numbers end in 6 or 8. Let's let n be an even perfect number. If we know that's true, then we know that n is of this form, this 2 raised to the k minus 1 times 2 raised to the k minus 1. This was Euler's result, so Gauss is picking up on Euler. Here's an aside, the exponent k must also be prime. So if k is equal to 2, then n is equal to 6, right? You can check that, so it's certainly true. If k is greater than 2, then n is odd, so k must be of the form. So it must be of one of two forms. If it's odd, it could be a 4m plus 1 or a 4m plus 3 for some m in the integers. So if it's if it's odd in a form 4m plus 1, then we can replace the k value here with 4m plus 1, the k value here with 4m plus 1. And what do we get? We get 2 raised to the 4m and 2 raised to the 4m plus 1. Let's see, so if I multiply this through, I get 2 raised to the 8m plus 1 times 2 raised to the 4m. And now factoring out just a 2 from this one, I get 2 times 2 raised to the 8m and 2 raised to the 4m. Associating the 8 with the 2 and the 4 with the 2, I would get 16 to the m and 16 to the 2m. And sorry, short interruption there, but 2 raised to the 8m could be thought of as 2 raised to the 4th to the 2m, and 2 raised to the 4th would be 16. So we can see that we can produce a 16 here and here, right? And now take a look at how 16 behaves in mod 10, right? So let's see, 16 to the first is equal to 16, it's 6. 16 to the second is equal to 256, it's 6. 16 to the third is equal to 4096 is equal to 6. So we could use induction and we could show that 16 raised to the t is always going to be congruent to 6 mod 10 for any t. So what do we have here? We've got, if we go back to our expression here, this is the thing that we're curious about. So we have that 2 times 16 raised to the 2m times minus 16 raised to the m must be equal to, well, 16 raised to any power, right, is going to be congruent to, and I'm using a congruent sign here, it's going to be congruent to 6, right? So we have 2 times 6. And then 16 raised to any power is also going to be congruent to 6. So we have 2 times 6 minus 6, so it's congruent to 6 mod 10. What does that mean? That means when this number, is divided by 10, it leaves remainder 6, right? So the last digit it's got to be 6 in this case. So what if k is equal to 4m plus 3? Well, if k is equal to 4, remember that k is is odd, right? And this is one way of distinguishing between two types of odd numbers. So if it's 4m plus 3, then what happens? Well, if we replace in our expression, if we replace in this expression here, the 4m plus 3, and add some exponents, we get 4m plus 2 here, we get 4m plus 3 here. Go ahead and distribute the 2 times 2 raised to the 4m plus 2 across. And what are we going to get? We're going to add exponents there, so 4m and 4m will make 8m, the 2 plus 3 will make 5, and the 4m plus 2 here. And now we'll kind of play the same game again. We'll try to create 16s. We know those behave like 6s, right? When incongruence mod 10. So we rewrite this one as, we take 1 power of 2 out and we write it as 8m plus 4. We take 2 powers of 2 out of here and we write it as 4 times 16 to the m, 4m. And here we can take a common factor of 4 out and write it as 2 to the 4th to the m plus 1 power. And the 2 to the 4th we can write as 16. And again, since 16 to the t is congruent to 6, what do we have? We're right here at this stage. We make a congruence statement mod 10. Then this 16 becomes a 6, this 16 becomes a 6. 2 times 6 is 12, 4 times 6 is 24. We get negative 12 mod 10, which of course has to be congruent to 8 mod 10 because the difference here has to be divisible by 10. So the last digit is 8 in this case. So what have we just shown? We've shown, let's go back real quick. If the exponent k is prime, then if k is 2, it's true. If k is greater than 2, then k is odd, and it must be of one of two forms. If it's of this form, we get something that ends in 6. If it's of this form, then we get something that ends in 8, using modular arithmetic as our machinery for the proof. And so you see that the invention of Gauss of theory of congruence proves to be pretty fruitful in terms of proving this statement, which was conjectured since ancient times about prime numbers, Mersenne primes in particular. And that's about all I have to say about Gauss. And I guess I'll just say I'll make these notes available to you, and wish you luck in your studies. And I will see you when I get back on Monday.